Let's use the tensor product representation of the quantum Fourier transform to construct quantum circuit diagrams. First, let's define the tensor product representation. Consider a computational basis state which is labeled by a string of bits. We can call those bits x1, x2, ... all the way up to xn. And this little n is the number of bits in this string. It's also the number of qubits in the circuit diagrams that we're going to be constructing. The quantum Fourier transform takes this computational basis state and it maps it to 2 to the power of minus n on 2. This is little n. And then we're going to have 0, so the state denoted by 0, plus e to the 2 pi I times 0.xn. And then we have 1 over here. So this notation over here is actually a binary string. So when we look at this and we see 0.xn, this is actually the 1/2 digit. So it's not the 1/10 digit. We're not dealing with decimal representations. We're dealing with binary representations. We are shifting this string by 1 unit. And that 1 unit is just going to leave this xn. And we're only interested in the fraction. We're not interested in the whole number, because the whole number is going to give us an integer multiple of 2 pi. And e to the 2 pi I is equal to 1. So this is the first part of our tensor product. The next part in our tensor product is going to have this format. We're going to have 0 and then e to the 2 pi I. We're going to have 0.xn minus 1 xn. So now we've shifted it 2 units, and we're going to have the state 1 over here, and we can keep going on and on and on until we get to the final state, the nth state, and that's going to look like this. We're going to have 0 plus e to the 2 pi I, and then 0.x1 ... all the way up to xn. So for the nth term, we've completely shifted this binary string, and we've shifted it, and it's less than 1. So we have 0 point the entire binary string. So this over here is equivalent to the decimal point, but we're dealing with binary. And over here we have the decimal point here and the decimal point here. So I'll close this bracket, and this is the phase factor that multiplies the state labeled by 1. So 0 and 1 are just labels for the computational basis states. So here we're dealing with 1 qubit, another qubit, all the way up to n qubits. So that's what this little n is denoting. Now that we have the general case, let's use this tensor product representation to construct some quantum circuit diagrams. So let's consider the first case, which is n equals 1. If we only have 1 qubit. Well, if we only have 1 qubit, then we can initialize that qubit in the state x1. So x1 is either 0 or 1. Those are the two options for this bit. And this bit is a label for the state of this qubit. Now that we've initialized the state in one of the computational basis states, we can apply the Hadamard. And when we apply the Hadamard, we're going to get 1 over the square root of 2 times 0 plus e to the 2 pi I times x1 over 2. And why is this the case? Well, if you cancel the 2's over here, what you'll see is e to the I pi times x1. If x1 is equal to 0, then we're going to have 0 up here, and this is going to turn into plus 1. But if we have 1 as the value of x1, then this is going to be e to the I pi. And that's equivalent to minus 1. So then we're going to have a phase factor of minus 1 in this superposition. We can write that as the Hadamard acting on the state 0 gives the state plus, and the Hadamard acting on the state 1 gives the state minus. So the Hadamard gate transforms the Pauli Z eigenbasis into the Pauli X eigenbasis. These are the eigenvectors. These eigenvectors have eigenvalue plus 1, and these eigenvectors have eigenvalue minus 1, when Pauli Z and Pauli X act on them respectively. So 0 and 1 is the standard notation for the computational basis, and that is the Pauli Z eigenbasis. And when we form these superpositions, then we're dealing with the Pauli X eigenbasis. A plus over here, that is a superposition of 0 and 1. And when we have a minus factor over here, that is a superposition with a relative phase of -1. So the Hadamard gate is actually the quantum Fourier transform for a single qubit. So if we just have one qubit, all we need to do is apply the Hadamard gate, and we've done the quantum Fourier transform. This is equivalent to 0.x1 using this notation. So we can just ignore all of these other terms. N is equal to 1, so we have 0.x1. So the Hadamard has the effect of having these factors of 1/2, which depend on the state of the computational basis state over here. Now, another useful quantity that we're going to need to define is the Rn matrix. And we're going to define that Rn matrix with omega sub big N. And omega sub big N is equal to e to the 2 pi I times big N to the -1. Or in other words, we're dividing by big N. And this is equivalent to e to the 2 pi I times 2 to the minus little n. That's because big N is equal to 2 to the little n. So the number of qubits determines the dimension of the Hilbert space. 2 to the power of little n is big N. And these are two different ways of defining omega sub n. And this is going to show up in the matrix R sub little n. So this is a diagonal matrix with entries 1, and on this entry over here we have omega sub big N. So this is a matrix that we're going to need, and it's going to be very useful in a moment. Now let's consider the case for n equals 2. So we have 2 qubits now. And these 2 qubits I'm going to call x1 and x2. So x1 and x2 are just labels for the states of qubits 1 and qubits 2. And when we take the tensor product of this, we're going to get this state. And we can ignore everything up to xn. We're only interested in 1 and 2. So that's what happens when we take the tensor product of these two guys. So when we initialize this in a computational basis state, we can apply the Hadamard gate, and then we're going to apply the controlled S gate. So this is S over here, and it's a controlled gate. And the value of x2 is going to control whether or not we apply this S gate. And then we're going to apply the Hadamard gate over here on the second qubit. And finally, this is going to give us something it has the incorrect order, so we have to apply the swap gate. And this is the notation for the swap gate. And when we apply this swap gate, we're going to get the correct order for these qubit states. And let's have a look at what happens up here. Up here is what we get from this bottom one, because we're swapping the states of the qubits. So that is just a single Hadamard gate. And that's going to give us 1 over the square root of 2. Then we have 0 plus e to the 2 pi I. And then we're going to have this x2 divided by 2. So x2 determines what happens with this Hadamard, whether we get a +1 in the superposition or a -1 in the superposition. It's just like what we have up here. And we'll close this bracket, and this is the coefficient of 1. Now, it's a little more complicated, the next part over here, because we have a controlled S gate. So we're still going to have 1 on the square root of 2. Then we're going to have 0 plus e to the 2 pi I times, we're going to have 2 terms. So first we have the Hadamard. That's going to be x1 over 2. And then we're going to have the effect of this controlled S gate. And this controlled S gate is going to depend on this x2. So x2 divided by 4 is going to occur over here. And this 1 on 4 factor, that is coming from this S gate. And I'll close this bracket, and then we're going to have the state 1, and we can close this bracket over here. So let's elaborate on what this S gate is actually doing, because this is related to this definition up here. If we consider the case where this little n is equal to 2, then we're going to have 1, 0, 0 omega 4. Okay, so we have omega 4, and omega 4 is actually equal to I. So this is 1, 0, 0, I. And this is, by definition, the S gate. So why is this equal to I? Well, if you put 4 as the value up over here, you're going to have 2 on 4, which is a half. So you actually have e to the I pi on 2. And e to the I pi on 2, that is equivalent to I. And you can think of it using this definition or using this definition. You can substitute a little 2 over here, so a 2 in the exponent, or you can substitute 4 for this value of n. And what you're going to get is I. So this is the S gate. And this over here is the implementation for the quantum Fourier transform if we're dealing with 2 qubits. So these guys determine, the values of these bits determine the computational basis state that is the input. That's what we're initializing this as. And then we're going to act with a Hadamard and a controlled S on this first qubit. And then the second qubit, we're just going to act with this Hadamard. And then we're going to swap the order using the swap gate, and that's going to give us this expression. So if we look up over here, we can ignore all of these terms and just focus on these two. What we're going to have is 0.x2. That's occurring over here, 0.x2. That's because n is equal to 2 for this example. And then in this term, we're going to have 0.x1, x2. So we have x1, x2. That is occurring in this little fraction example over here. So this notation is very convenient for expressing these binary strings and instead of writing out these long fractions. So this 4 over here comes from this definition, where we have 4 over here and 4 in this coefficient. So we have a factor of 1/4. And that factor of 1/4 depends on whether we have a 0 or a 1 over here as the value for x2. So that is why this is the control qubit and this is the target qubit. So this is how we implement the quantum Fourier transform using a quantum circuit diagram if we're dealing with 2 qubits. Now let's have a look at the 3 qubit case. And then we'll be able to see a pattern emerging. So for n equals 3, this is the 3 qubit case. What are we going to have? First, we need to initialize all of the qubits. So we're going to have the qubits initialized in x1, x2, and finally x3. So these bits are labels for each of the computational basis states. And then when we take the tensor product of all 3 of these guys, we get the computational basis state for the collective 3 qubit system. So that tensor product allows us to smush all of these Hilbert spaces together into a single big Hilbert space. And the dimension of this Hilbert space is actually 8. We're dealing with an 8-dimensional Hilbert space. That's because 2 to the power of 3 is equal to 8. So now, once we've initialized, first we're going to apply a Hadamard gate. So that's always the first one. And then we're going to apply a controlled S gate. And the control is going to go down over here. So x2 is going to determine whether this S gets applied. And then we're going to have a T gate. And I'll define the T gate in a moment. So this is a T gate. And this is a controlled T gate. We're going to drop this control wire down over here. And the state of x3 is going to determine whether or not we apply this T. Now, let's have a look at what happens to this middle qubit. That's qubit 2. We're going to have H. And then we're going to apply S. And we can drop down a control qubit. So this is the controlled S. And then finally, we're going to apply a Hadamard over here. But there's a problem. The order is going to be incorrect. So we have to implement a swap gate again. So I'll continue this over here and this over here. And then we're going to need a swap gate. So this is the symbol for a swap gate. And we're just going to swap the first and the last one. The middle one is okay, but it's just the order of the first and the last that are incorrect. So now that we've applied this swap gate, we have this correct order. It's the correct format that we're looking for. So let's have a look at what all of these states are. First, let's have a look at this top qubit. This top qubit is actually the state of this bottom line over here. So we've taken this bottom line and then we've swapped it, so now it's in the top. So we have 1 over the square root of 2, then 0 plus e to the 2 pi I. And what do we have? We have just a single Hadamard, and x3 is the input over here. So we're going to have x3 on 2. And that's the coefficient of the state labeled by 1. Next, we're going to have 1 on root 2 times 0 plus e to the 2 pi I. And what's happening in this middle state? Well, first we apply the Hadamard, and then we apply the controlled S. The Hadamard, that's affected by x2. So x2 is the coefficient of 1/2, and x3 is the coefficient of 1/4. So x3 is the coefficient of 1 on 4. And this is the coefficient of 1, the state denoted by 1. And then, what about this final one? That's actually what we have up here. That's all three of these terms. That is 1 on root 2 times 0 plus e to the 2 pi I. And then we're going to have first x1. So that's x1 on 1/2. That 1/2 comes from the Hadamard. And then the controlled S is going to give a quarter, and the quarter is going to be controlled by x2. So we have x2 over 4. And then finally we have x3 over 8. That's the next power. So this T-gate implements a 1/8 factor over here, and it depends on x3. So if x3 is equal to 0, we're not going to turn this on. But if x3 equals 1, then we will apply this over here. So this multiplies the state 1, and we can close the bracket. So you can see where this normalization coefficient out the front is coming from. Every time you have one of these terms, you get a factor of 1 over the square root of 2. So that's where this comes from. That's why we have a little n up in the top. So every one of these guys gets smushed into one factor, and that is the normalization coefficient. So we can write this in decimal format. We can see that this is 0.x3. So that would be n equals 3 over here for this case. So we have 0.x3. And then the next one is 0.x2x3. And then the last one is 0.x1x2x3. And this is the entire sequence over here. So we have x1, x2, x3, and then we have 0.x1, x2, x3. That's exactly what we see in this format over here. The final one has the entire bit string shifted all the way after this point. So this is another way of expressing this, and this is more suggestive because we can see the factors that are appearing over here. These are powers of 2 in the denominator. Now let's unpack what this t is. So t actually corresponds to R3. And R3, if we look up over there, R3 is the same as 1, 0, 0, omega 8. So this 8 is 2 to the power of 3. And we can write this as 1, 0, 0, e to the I pi on 4. Why is it 4? Well, it's because we have a factor of 2 over here. So if we have 2 on 8, that's going to give us 1/4. And what is this equal to? Well, we can write it out in the Cartesian form. This is the polar form of a complex number. We can also write this as 1, 0, 0, and then we have 1 plus I over root 2. So this is the same as 45 degrees. We have a point that's on the unit circle in the complex plane, and it's at a 45-degree angle. So the cosine and sine of 45 degrees, they give this value of 1 on root 2. So that is why we have this Cartesian form. And this is equal to t. That is this gauge, t. So now we've seen what R3 is. R3 is equal to this t. And then if we wanted to keep going, we would have R4, R5, R6, all the way up to Rn. And every time we add an extra qubit, we have to add an extra chunk that looks like this. But we have to add an additional controlled phase gate. So all of these are phase gates. They apply a phase to this one state over here. So the coefficient is a phase factor. And you need to keep adding more and more phase gates that have a controlled wire. So all of these are controlled phase gates, which strategically are placed here to give us exactly the right phase factor that matches this definition. And the problem with this setup is that it gives you the incorrect order. So every time you perform this setup, you have to then do swaps. So you have to swap the order of these qubits so that it matches this standard format for the quantum Fourier transform. So in this video, we have seen 3 examples of the quantum Fourier transform. One for a single qubit, 2 qubits, and 3 qubits. And now you've seen the pattern and how to actually assemble these quantum Fourier transform circuits. Now, what is the motivation for this? This is actually a really, really important algorithm to be able to implement on a quantum computer. In fact, it is used in Shor's algorithm, and we will see that in later videos.